Hello, how is everyone doing? I hope everything is okay over there. So please stay safe and healthy. And don't forget to wear a mask and wash your hands. Well, this is going to be the first time that we do this online teaching and learning, right? So I'm going to talk a little bit about this. It's going to feel strange and funny at the beginning because, to be honest, this is quite new and unexpected to me. I didn't expect that I had to start doing this right away, and a lot of things are not ready. Even with the tools I have, I am pretty new to this. So I'm gonna try my best to provide you with this lecture. If I make any mistakes, don't laugh, and just cut me some slack. Just think that I'm new to this. I'm not like you guys. Okay, so about the situation, I'm not going to talk about that because you have heard the news every day and maybe too much already. So it doesn't really matter now. It is what it is. We have all these tools and technologies. We are lucky that we can keep going without having to come to class. So there is no need to stop the progress that we had so far, even in this kind of situation. So now let's get started now. By the way, this slide that I use here can be downloaded from Canvas and also from the Line group. I am going to post this on there, so I recommend that you download and study along with me. Don't leave it until the last minute, otherwise it's gonna get overwhelming. Okay, back to math, to calculus. So today's topic is going to be about the double integrals. Yes, we have talked about this last week on Wednesday, but I'm going to teach you a little bit more about this so it becomes clear to you about how to manage the double integrals when it gets tricky. Okay, so last week we talked about this. We talked about the physical meaning of double integrals. All right. The physical meaning, and we also talk about the comparison to the single integral, the comparison compared to single integral. When we did that, we mentioned about this single integration of a single variable function fx, and we integrate this. Let's erase that. Okay, this works. Okay, now with this, and we integrate this function with respect to x, right? So we establish that when we do this, this is going to be equivalent to the area. Not equivalent, it's related to the area under fx, and you have to keep in mind that in this case the fx we have here is a curve. Alright, it's a curve. Alright, so with this I added something more to this physical meaning of the integration of fx. So I add that this area can be both positive, and negative, and since it can be both positive and negative, it means that it can cancel. Alright, so whether it's positive or negative, it's up to the sign of the function value. If the function is positive, the integration that you get is most likely to come out positive. But if the function is negative, then you can expect the integration to come out negative. Now, we know that this is the area under the graph, but in order to find the area, it's impossible to do that without knowing the boundaries. We need to know where this area starts, and we need to know where this area ends. And in this case, we use this boundaries. X start at A and ends at B. In this case, we have the boundaries for the area that we want to compute. Okay, and that is it for the single integration. But then we move to the double integration, and double integration works on, we perform that on two variables, a function f(x,y), and we perform this double integral. In this case, I'm going to perform integration with respect to x first, and then we can't just stop here. We have two variables, so do that again with respect to y. And last time we talked about this, and we established that this is the volume How do you guys use the digital pen? It's so hard to use. Maybe those of you who can use well can teach me how to do this. Okay, back to this. This is the volume of under f(x,y), and at this point you should know that f(x,y) is a surface, just like you see in this graph. This surface green is the f(x,y), and under this surface, or this sheet of surface, you can see that you can see the volume under that. And once again, it's going to be similar to above there. This volume can be positive and negative depending on the sign of your function, and of course it can cancel. So if your double integral comes out to be negative, don't be surprised and get confused about it. It's possible. And if the double integral comes out to be 0, it doesn't always mean that the volume is 0. It could mean that it cancel each other out somewhere. Okay, so with this, okay, let me change this a little bit. This is too big. I'm going to change this boundary A and B over here. So above here, for single integration, in order to find that, we need to know the boundaries, and it's going to be the same thing with double integrals. Alright, so in this case, I'm going to use the notation R. I'm not going to put A, B, C, D right now. I'm going to put R. Alright, this stands for the boundaries for this this volume we are talking about. You know, we have volume, we need to know the base. So when it comes to R, I want you to think of the base of the volume. Base of the volume. And another thing about that, it has to be on XY plane. So when it comes to this R, expect something on XY plane. This R can be called by another name, and that is the domain. Domain of double integral. Okay, and this is the same as R. This is different from the domain of a function. Domain of a function is the value of the variable that makes sense, right? That doesn't create the division by 0, square root of negative value, or log of 0, something like that. So with this R is the domain of the double integrals. I want you to pay attention to this. This domain R can comes in many forms, in any shape. Alright, so the first thing, it can comes in any shape, but we can categorize this into two main categories. The first one, the easiest one, is the rectangular shape. Alright, and 2, it's going to be non-rectangular, but I'm going to call it general. So first, rectangular domain, and second, general domain. So with the rectangular domain, I told you that this is easy to manage. Sort of easy to manage. Okay, and you can see in the next slide why it's easy to manage. But before that, I want you to take a look at this. We talk about this region R, right? And we talk about that this R is the base of the volume. So I want you to see this. In this example, this area under the surface had this base. It looks like this. Right? This shaded area. And you can see that X start at A right here and ends at B. And what about Y? Y start at C right here and ends at D. So this represents the base of the volume, or the domain of this double integral. And with this, you can see that the base is rectangular. So this is going to be the first type of the domain. I'm going to write it. So last week we worked on this, and we have this double integral f x y. Okay, with respect to x first, maybe right now. Okay, and then with respect to y. And when we integrate with respect to x, I want x to range from A to B. And when we integrate this with respect to y, we want this to range from C to D. So that is the first form of double integral that we saw last week. Keep in mind that this is the easy one, the rectangular base, right? And this is going to be related to Fubini's theorem 1 on the next slide. But also keep in mind that this base can be more complex, can be non-rectangular, can be curvy, can be parabolic, can be exponential, and that's going to be in the general domain. I would say that this is tricky. But if you understand the how to manage it, it's not going to be too bad, in my opinion. Alright, so let's move on to the next slide. Fubini's theorem 1. So let's take a look here. So this is all about the double integral, and we can see that the meaning here is that we want to perform double integral on a certain region R. And in this case, this region R is rectangular. Alright, and that's why we have these boundaries of A, B, C, D. We see that X has to range from A to B, and Y has to range from C to D. Just like in the last slide, we see this rectangular base on the ground. And since it's the same base, it doesn't really matter whether we integrate X first or Y first. So that's why we have this relation between these two double integral equal, because just like before, it's the same base. Whether it's dx dy or dy dx, it comes out to be the same. But if you switch, don't forget to switch the integration to. So in this second terms here, the y has to start from C and D, and then x A to B. Don't forget to swap that. Now, with this, it's equal, but in terms of execution, it's a little bit different. And it's important that you know how this difference works, because it's necessary for you to understand the general domain. So let's take a look at the difference between these two, even though the result is the same. So let's plot this. Oh. Okay, I want a straight line. Alright. And this. Okay, this is going to be the first double integration with respect to x first. But before that, let's draw the region that we want to the domain region. So we know that x starts at A and ends at B. C for y, start at C and ends at D. X-axis and y-axis. So we know that the region that we want to find the volume on is this region. Okay. Well, you can make shaded here, and you can do the same thing with the other double integrals. Here we have this same thing, range from C to D, and x ranges from A to B. And you can see that the base exactly the same, right? Okay, y-axis and x-axis. Now, how is it different? The result is the same. It's this same rectangles. So let's take a look at how the integration is done. So let's take a look at the first double integral with respect to x first. I want you to pay attention to this. Looking at this, we integrate f, the function, with respect to x first. It means that we are going to combine all these x values. We are going to work on the x values. So it's basically we are going to sweep horizontally when it comes to x-axis. It's horizontal, right? So we are going to work on x horizontally. Sorry, we are going to work on this region horizontally. So starting at y equal to c, so we are going to sweep the x value, right, until x equal to b, starting from a to b. And then after we are done with this line, we are going to move further up and do the same thing. Sweep from A to B all the way through. Wow. And ends at y equal to D. Okay, so this is how it works. Now, on the right hand side, on this graph, compared to this, let's take a look at this. This is integration of the function with respect to y. We are working on the y variable. When it comes to y variable, it's along the y-axis. This is something that is doing that you have to do vertically. So we are working on y variable first. So we are going to sweep vertically. So starting at x equal to a, we are going to integrate with respect to y, sweeping the y value from C to D, from C to D, and keep going until x equal to b, and that is the end of the integration. Well, the result here is the same for the rectangle, but it's not going to be the same for the general domain. So you might take a note here. Same result for rectangle, but not always for the general domain. And we are going to see why really soon. Okay, sweeping is all about this slide. Sweep x first and sweep y first. Now let's move on to the general domain. Now here's the thing. This is the point of this lecture. It's all about the general domain. Okay, before anything, I would like to note a couple of things about the general domain. So put this. When it comes to general domain, it's non-rectangular. So you expect something to be curvy, you expect it to be irregular. Curvy, Oh man. And irregular. Okay, and the next thing you need to know about this is that the order of the integration usually cannot be swapped, interchanged directly. Order of integration cannot be swapped directly. So we can't just swap it, just like in the Fubini's theorem 1. That's not going to work here. So the last thing you need to know is that, oh, hold on. Well, I think just two things that are important. So just keep it like this. Now, okay, in order to understand the general domain, let's categorize it. Let's make it easy to identify it. So let's say that this general domain, it has two types, type 1 and type 2. Type 1, the property of this type 1 is that the domain bounded by two curves, all right, one from below and one from above. So here's the key. Type 1 of the general domain, you have two curves, one from below and one from above. And for type 2, your domain is going to be also be bounded by two curves. Domain bounded by two curves, but in this case, one from the left and one from right. So you see the main difference here. One is you see two curves, you see two lines, lower and upper. The other type you see on the left and on the right. And in order to deal with this, it's going to be a little bit different. For this type 1, you are going to sweep x variable first. And for this type 2, you are going to sweep, for the type 1, you are supposed to sweep the y variable first, y. And then for type 2, you are going to sweep the x variable first, x variable first. Okay, at this point it might not make sense, but let's take a look at some illustration why type 1 requires you to sweep y and why type 2 requires you to sweep x. Now let's take a look at type 1. Type 1, I told you that we need to sweep y variable first, but let's take a look at the property first. Before that, here I told you that type 1 is going to be to have two curves, one from below and one from above. So you can see these two graphs here. These two graphs has a lower boundary by this curve. I'm going to call it lower function, all right, and it's denoted by g1x. Same here with this graph, looks a little bit different, but with the same sort of properties, bounded below by a curve called g1x. Okay, and then bounded above by another curve called g2x. This same thing, bounded above by g2x. if you see this kind of shape, like one from below, one from above, you know it's type 1. Alright, and type 1, it says that you need to sweep the y variable first, which means that you integrate with respect to y first. So let's do that. We have this multi-variable function f(x, y). You need to integrate this with respect to y first. Alright, and then followed by x. Okay, so this is the starting point. But then we need to specify the boundaries for this region that we want to find the double integral. So okay, so let's take a look at this. The first set of integration with respect to y. You are going to see that this is about integrating y variable. This is about sweeping y variable. So if you look at the graph, this is like sweeping y variable from this starting point to the end point up here. And once we are done at this, we are going to move on to sweep up. Okay, keep going just like we did with a rectangular domain all the way through. And same for this. I'm going to do this quickly. Okay. Alright. So with this in your mind, you can see that this sweeping starts from the lower function, right? From the lower function right here, and ends at the upper function, which means that the y value is going to sweep starting from the lower function, which is g1x, and ends at the upper function, which is g2x. Okay. Alright, and then for the x variable, all we need to do is to tell the whole range of this sweeping. Alright, so we can see that x variable starts at a and ends at b. So we can just put it here. X start at a and ends at b. You don't need to worry about the sweeping in the x direction because all the sweeping has been done through y. We have taken care of the irregular sweeping, starting from lower function and ends at upper function. And for x variable, we just specify the whole range. Okay. Alright, that is the first form of the general domain double integration. Okay, so let's move on to the type 2. Type 2, sweep x variable first. Let's see why. So here we have this these two graphs, and let's take a look here. There's something different about this than the one we saw in the last slides. So here I can see that I have one curve, one boundary on the left hand side, same here on the second graph, and I also have another boundaries, curvy boundaries on the right hand side. Same here. When I see these two boundaries, I am going to connect them with the sweeping. So I'm thinking about sweeping from this the left, sorry, sweeping from the left function to the right function like this. Left from the left to right like this. Now back to the type 2 sweep x variable first. What this means is that we need to integrate x variable first. It's all about sweeping the x variable. So we have this function f(x, y), and we are going to integrate this with respect to x first. and then we do that again with respect to y later. Okay, now down here we sweep from the left function to the right function, and we are going to keep doing this all the way up here. Alright, so in terms of the formula, we sweep the function x variable first, starting from the right function, which is called h1y, and we end at the left hand function that is called h2y. Okay, and the whole range starts from from y equal to c and ends at y equal to d. Whole range starts from c and ends at d. So we can see that here, when we integrate with respect to y, all we need to do is to go from c to d. All these sweeping has been done with the x variable. Same here. Okay, so you can see that the difference between the type 1 and type 2. For type 1, you need to sweep vertically, and for type 2, which is this one, you need to sweep horizontally. When to use type 1 or when to use type 2, it depends on the problems. You have to look at the shape of the domain in order to determine. So make a note here. Determine type before proceed. If for any problems you start and you don't know what the type of this domain is, don't go any further. The first thing you need to know is that what kind of shape it is and which type is it going to be, so that we know what to do with it. Alright, so first thing, draw the graph, draw this domain, and determine the type. And then you know which formula to use. Okay, so why don't we start, why don't we do some examples on this? Oh, okay, so this is Fubini's theorem 2 that is related to the general domain. So you might make a note here. This is for general domain. The theorem 1 is for the rectangular domain. Theorem 2 for general domain. So to type 1 here, you are going to sweep the y variable first. Alright. And this is going to work when you have one function below and one function above. So this is g1. You can make a note here, this is lower function. And g2 here is the function above. I'm going to call it upper function. Now we have type 1. We also have type 2. Type 2 is different in the way that we are going to sweep the x variable first. Sweeping x, sweeping along x-axis. This is sweeping horizontally. Well, up here this is vertically. Down here is horizontally. Okay, sweeping horizontally, it has to start from the left hand side and ends at the right hand side. So h1 here is the start, that is the left function. And up here is the right function, the end of the sweeping. Okay, so that is Fubini's theorem 1 and theorem 2, one for rectangular, one for the general domain. So I think you are you are overwhelmed by all these explanations. So let's do some examples. Alright, so example 1. So let's do this together. So we would need to calculate the double integral. And we can see that the function that we have, the surface that we have, is x plus 2y. And we need to do this over a domain D, and it's bounded by the parabolas. The first one is y equal to 2x squared, and the other is y equal to 1 plus x squared. And let's assume that you don't have the picture on the left hand side. If you only have the text here, then you just don't know how are you going to proceed, because you don't know the type of this domain. So let's assume that we don't see the graph right here. So just the first thing we need to do is to determine the type of domain, because it's likely that in the exam you are not going to be given with the graph. You are going to be given with just the equation. So let's take a look at the first parabola, which is the y equal to 2x squared. This is like a regular parabola, but a little bit steeper. So let's draw that. I'm going to draw it along with the one that we had on the left. So this is the steep parabola. It's going to be this one. Okay, so I draw that. And then I'm going to draw the next parabola, which is y equal to 1 plus x squared. So this is regular parabola, but shifted up 1 unit. And it's going to be drawn by this red line. And as you know, this point of intersection happens at y equal to 1. So we have this shape, these two curves drawn on the graph. And then you can see that with these two curves, we can see the enclosed area like this. And once we see this, we need to determine the type of the domain this one is. So let's ask ourselves, when you see this, do you see a function from below and below and above, or do you see a function on the left and the right? Well, if you look at the same thing as I do right now, you are going to see that, hey, I have this function on below here, right, down here, and then I have another function up here. So one from above, one from below. So definitely this one is type 1. And type 1, I'm going to need to sweep y variable. And you can see that for this, we are going to sweep y variable. All the way through. Okay, so let's set up the integration. So we have this x plus 2y, and then we need to integrate with respect to y first. Alright, now we need to specify the beginning and the end. So I'm going to sweep y variable from the lower function, and the lower function is 2x squared. Oh, okay, make it red, 2x squared. And then I'm going to sweep to the upper function, which is 1 plus x squared. Alright, now the sweeping is done from lower to upper, but then I need to specify the whole range of the integration, the x value. Without the graph, I don't know where x starts and where x ends. So it's important that we determine this starting point and the end point. So let's take a look here. We have two functions. One is y equal to 2x squared, and the other is y equal to 1 plus x squared. we want to find this intersection right here on the graph. That is the starting point right here and the end point right here. I know that the graph tells you that it's minus 1, 2 and 1, 2, but let's assume that we don't have this graph. We need to determine this by ourselves. So to determine this, the intersection between these two equations, we need to solve them together. So I'm going to substitute 2x squared into y. So here we have 2x squared equal to 1 plus x squared. Here we have x squared equal to 1, and we know that x equal to minus 1 and 1. You can continue to plug this into to the equation, and you get, for this minus 1, y equal to 2, and for this x equal to 1, y equal to 2 as well. But we don't need that. All we need is this, the range of x, so that we know it starts from minus 1 and ends at 1. Okay, so important part: lower function 2x squared, upper function 1x squared. From now on, it's just the integration. Alright, so I told you about the guideline how to do double integration before, so I'm gonna repeat again. First guideline: work from inside to outside, inside to outside, and 2, treat other variable as constant. Alright, so the first thing I need to do is to integrate this x plus 2y with respect to y. So I am going to treat x as a constant. So integrate this with respect to y, it becomes xy, and integrate to y, this becomes y squared. Okay, so this has to be evaluated at 2 points, 2x squared and 1 plus x squared. Right, and the integration outside has to stay the same. Integrate from minus 1 to 1 with respect to x. So we are going to start from this and continue. Alright, I have some space here. Okay, so we are going to substitute 1 plus x squared into y. Don't make a mistake here. We are working on y variable. So this x stays the same. 1 plus x squared goes to y. Alright, plus, now 1 plus x squared goes to y, 1 plus x squared. And we have the square along with it. So that's the first term. Minus the other terms. 2x goes in. This becomes 2x cubed. 2x goes in. 2x squared, sorry. 2x squares go in as y. Alright, so we have everything. Integrate from minus 1 to 1 with respect to x. Let me check if this is correct. Alright. It's a lot of numbers. I don't want to make a mistake and re-record everything again. Alright, it seems everything is fine. Now let's continue from this. So we have this integration minus 1 to 1, and we have this x plus x cubed plus 1 plus 2x squared plus x to the fourth minus 2x cubed minus 4x to the fourth dx. And now let's combine everything to make it easier to do integration. Minus 1 to 1, so we have 1 plus x plus 2x squared minus x cubed minus 3x to the fourth dx. Okay, let me double check. Okay, 1x 2x squared minus x cubed minus 3x to the fourth. Alright, so it's correct here. Now we need to continue with the last integration, and this one is easy because this is single variable. So let's do that. Integrate 1 becomes x. Integrate x becomes x squared over 2. This becomes x cubed over 3. This becomes x to the fourth over 4. This becomes x to the fifth over 5, and evaluate it from -1 to 1. I'm not going to put the numbers in here. I'm going to use a calculator, and this comes out to be 32 over 15. Alright, so this is how it's supposed to be done, and keep in mind that this is for type 1. Okay, type 1, two functions below and above. Alright, so this is the result for these problems. But now we are going to make a challenge for ourselves by doing the same thing, problems, but with different domain. So I'm going to move to example 2. Okay, example 2, we are going to repeat example 1, but perform the integration over a different domain. This time around, this domain is this: parabola x equal to minus y squared plus 4, and another straight line y-axis. This time it doesn't give us the graph. We just don't know anything. Oh, one thing we know is that it's a repeat, so fxy, it's going to be equal to x, it's going to be equal to x plus 2y. X plus 2y. That's all we know. But then, if we don't plot, we don't know the type, we can't continue. So first thing, determine type. To do that, you need to plot. So I have this. Okay. Now I know y-axis is easy. I have this y-axis ready to be used, but then we need to plot that x equal to minus y squared plus 4. So this is y-axis, and this is x-axis. Let me check if the recording is still going on. Alright. Okay, so y-axis, not a problem. The problem is this x equal to minus y squared plus 4. I want you to think about this. X equal to y squared, that is parabola on the side, right? But this is minus y squared, so it's going to be on the side and opposite way, and it's going to be shifted up 4 units. So I want you to think about this, and if you think hard enough, you should be able to see that it's going to be a parabola on the side and shifted up 4 units, and it should look like this. Okay, 4 units, and 1, 2, 3, 4. I don't know about this intersection yet. We can find that out later. So with this, we have this enclosed area, this curve that we just draw, and the y-axis. It's going to look like this one, this shaded area. This. Okay, now we see this area. We need to ask ourselves, do we see a function from below and above, or do we see a function from the right and the left? If you agree with me, you would say that, hey, I see the function on the left and the right. The left is the y-axis right here, and the right is the this curve, the parabola on the side. When you see this kind of shape, it's not a graph from below, it's not a graph below and above. It's obviously right and left. So with this in mind, you know this right away. With this graph, you sort of know right away this is type 2. Type 2 means that you need to swipe the x variable first. Starting from below here and going up. Alright, all the way through. So let's construct the integration. Alright, integration, we need to integrate the x variable first, type 2. So we have the same thing, x plus 2y, but we need to integrate with respect to x first. Now, when it comes to type 2, we need to specify the left-hand function and the right-hand function. The left-hand function, we know that is y-axis, and that is x equal to 0. The right-hand function is this parabola. So we know it ends at this parabola on the side, that is minus y plus 4. Okay, so now the boundaries for the x is done. What we need to do is to find the boundary for the y-axis. Oh, not the y-axis, for the y variable. So we need to determine this starting point and the end point of this integration along y-axis. So looking at this, we don't know. So let's solve the equation. So we have x equal to minus y squared plus 4, and we also have x equal to 0. We want to solve these two equations at the same time. So let's substitute x equal to 0 to here. So we have 0 equal to minus y squared plus 4. And you can see that solving this, we have y equal to 2 and minus 2. So we have 2 right here, minus 2 right here, and 2 right here. So we know y has to range from minus 2 to 2. Okay, now that we have the formula ready, we can perform the integration. We are going to integrate this with respect to x first. So we are going to keep y as a constant. So here we have x squared over 2 plus 2yx, right? Integrate that with respect to x, and we need to evaluate this at 0 and minus y squared plus 4. Integrate with respect to y, still the same, minus 2 to 2, and dy. Okay, now let's continue with that. We need to substitute that minus y squared plus 4 in place of x. So it's going to go in, becomes minus y squared plus 4. This is x squared, right? So square here over 2 plus 2yx, x now equal to minus y squared over 4, minus y squared plus 4. So substitute that in, minus y squared plus 4. Okay, that's the first term, and the next term is, well, 0 goes in as x, and we have 0 here and plus 0, so nothing. So integrate that with respect to y from minus 2 to 2. Alright, we continue from this. So here we have y to the 4th minus 8y squared plus 16 divided by 2 minus 2y cubed plus 8y. Alright, and we integrate this with respect to y from minus 2 to 2. Okay, this is going to be equal to y to the 5th, right? Integrate over 10. minus 4y cubed over 3 plus 8y and minus 2y to the fourth over 4 plus 8y squared over 2. Let me check if this is correct. So we have y to the fifth over 10 minus 4 over 3 y cubed plus 8y. Alright. Okay, that's correct. And so here we have to evaluate this from minus 2 to 2. So in the end, it's going to come out to be equal to 17 1 over 15. Alright, that is the answer for this problems. There might be a problem with this minus sign, but the whole process is still the same. Okay, let me check about this 17 1 over 15 again, but you might check along with me, but I'm gonna update on this number later because it's a little bit different from what I have here. Well, I'm gonna end this video right here because I don't want it to be too long, but this week I'm going to have another video, and it's going to be the case when the domain is not so obvious whether it's type 1 or type 2. In these two examples, it's obvious. The first one is type 1, the second one is type 2, but next one we are going to see sometimes we have to decide whether to use type 1 or type 2. It's like we have a choice. So I'm going to try to finish that as soon as I can. I'm going to end this video right here.